In this chapter, we will be looking at logarithms. In this lesson, we'll be converting between exponential and logarithmic forms.
So in a previous lesson, we had looked at how logarithms are defined, where they come from, and you noted that it was the inverse of the exponential function. Okay, but even having done that, so here's our exponential function, y equals b to the x. We took the inverse of that, we get x is equal to b to the y, and then there's this equivalent form, this and this log base b of x is equal to y. Turns out these are identical. Okay, these are doing the exact same thing. So there's an exponential form and a logarithmic form to this inverse. Okay, so here's this exponential function. It has an inverse that is in the form of an exponential, but it also has an inverse that's in the form of a logarithm. And we did a little bit going back and forth. Well, actually, we typically just went forward with that one. So now what we want to do is we want to practice going back and forth, okay, switching between those two, because it turns out that's a really important tool, or algebraic tool, I should say. Being able to convert from one form to the other helps us solve equations, and you'll see that in a little bit here. But first, we want to get used to this idea of going back and forth. So what we're going to use this common log function to complete the table of values below. So just look at what they did here. 1. We want to get a value of 1. So how do we do that in an exponential form base 10? Well, we make that 10 to the 0. So 10 to the 0 is 1. And the log form of that statement here is log of 1. The log base 10 of 1, common log of 1, is 0. So here, how do I get 10 out of that? Well, I make this 10 to the power of 1. And that means, okay, the common log base 10 of 10 is going to equal 1. Because remember, the logarithm is the exponent. The logarithm is the exponent. So here, 10 squared is 100. That's where I'm going to get 100 from. So this means the common log, the log base 10 of 100, is equal to 2. Because again, the logarithm is the exponent. Over here, 1,000 is 10 cubed. And so that means the log, or the common log of 1,000, is equal to 3, because a logarithm is the exponent. Okay? As long as the bases are the same, base 10, base 10, base 10, base 10, and so on, okay? Then we can make that comparison there. So if each x value is written as a power of 10, then there was a relationship between the y value and the exponent on each power, okay? In order to evaluate a logarithmic expression, we have to determine the exponent that must be applied to base 10 to get each value of x. And that's what we're doing here, because that becomes the value of the logarithm. And you're seeing that down here. And so all this is a statement of what I've just said up there. So here's the rule then. And let's zoom in on this, because this is important. Log base a of y is equal to x. It's because the bases are the same, okay, and the logarithm is the exponent. So then whatever that base is, that's what I'm going to put. Whatever that logarithm equals, that goes up into the exponent. And then I'm equal to the argument of that logarithm. And there's little things you can use to make this easier to memorize, if you will. But just really remember, focus on the fact a logarithm is an exponent. Okay? So, that being said, there are some rules, like it says right here, there are important rules that are not going to be given to you that you should know anyway. Okay, it's a little tight, but actually everything's on the screen there that you need to see here. So first of all, the log base a, doesn't matter what the base is, doesn't matter what a is, the base can be anything here as long as it's positive, not 1, okay, of 1 is going to equal 0. And that's always true because whatever that base is to the 0 will always get you a 1. That's just a rule, okay? Log base a of a is equal to 1. Since in exponential form, a is equal to a to the 1. Now these next two are a little less obvious, okay? But here we go. Log base a of a to the x is equal to x. Now, think about it. This is what's inside the logarithm here. And the reason that's true is because in exponential form, you'd go base to the exponent. So a to the x equals a to the x. Well, now, see, it's obvious over here. This is not such a straightforward way to write that relationship. So you just pay attention to that. You need to know that. Okay, what this really is saying here is that the logarithm, okay, the log base a, and the power of a are inverses of each other. And they're canceling each other out here, so I'm not going to come back to this in a second. It's very similar to me writing the square root of x squared being x. These ideas of the square root and the square there, they're canceling each other out. You're just left with x there. Very, very similar sort of pattern of thinking going on here. Additionally, we got a very, very similar pattern going on right here. Okay? Now, this one here is maybe a little harder to see, but a to the log base a of x is equal to x here. Now, I will show you why this works, but it's almost so quick, it's hard to pick up, and I'll show you here. I'll just erase this, and I'll do it in this little space here. So if I've got a to the log base a of x, I'm saying I don't know what that is equal to. Okay, I haven't got a clue here. Well, let's face it here. The issue here is this logarithm in the exponent. Okay, that's the best I can say. That is the problem here. So let's just let that equal y. We'll use a new variable to equal that. Okay, so y is equal to log base a of x. And so really what's going on here is I'm just going to make this a to the y. That's all I've done. Okay, I just renamed it. That's it. But now take this right here and let's convert that to the exponential form. So a to the y is equal to x. A to the y is equal to x. And there we go. That's our answer because there's a to the y. That's what I did. And so I know that that must equal therefore x. And if a to the y equals x, a to the log base a of x is equal to x. I know that is almost too quick of a proof to really see how that works there. But really that's the rule here. And again, and if you're really struggling with that, just think of it like this. This is a power. Okay, this is a power. The log is in the exponent. Okay, a logarithm is an exponent. And so in essence, they're canceling each other out, and you're just being left with that little x right there. Okay, so now anyway, let's take a couple seconds here and start to answer some questions, maybe using the calculator and trying to apply this idea of moving back and forth between these two different forms.
Evaluate each of the following to the nearest hundredth.
Okay, so we just got to evaluate some logarithms here. So here we go. This is the common log of 20. Now, I wish I could tell you that 20 was some sort of power of 10. The base here is 10, but 20 isn't a power of 10. So let's just do log of 20 and see what we get. And the question said round to the nearest hundredth. Evaluate to the nearest hundredth here. So what do we get? We got 1.30. So that's, my calculator's got that common log. So this is going to be approximately 1.30. Good. Take a look at this next one. Log of 45. Okay, well 45, once again, 45 isn't a power of 10. So I'm just going to use my common log feature on the calculator here. And I get 1.65. There we go. So approximately 1.65. So now let's just talk about what we're saying here. What this means is that if I take 10 to the 1.30, this should be approximately 20. If I raise 10 to the power of 1.65, that should be approximately 45. Now let's just check those. Okay, let's just check those. So if I've got 10, and now I'm just going to do this approximately here, just to show you here, because that's my 1.30. I could pull that number right out of here again, but let's just watch this. Okay, look at that, 19.95. Yeah, that's approximately 20. 10 to the power of 1.65. This should be approximately 45, and there it is, 44.668. Rounds to 45. Good. There we go. Now over here, this is a little different, because notice that I can rewrite 49, okay, as a power with a base of 7. And when that's true, okay, well, let's slide up here. If you've got log base a of a to the x, okay, so that's, here we go, log base 7 of 7 to the x, this must equal that exponent, so 2. And there you go. Over here, we're getting the exact same thing. Okay, 243 is in fact a power of 3. It's 3 to the 5th. Okay, and again, here's that pattern, log base a of a to the x. And we know that this has to equal x. Now in this case, that x is 5. So log base 3 of 3 to the 5 is equal to 5. Now if you don't know that 343 is a power of 5, you just got to play with it a little bit. Okay, but let's say that you're looking at this. This one here is probably less obvious than this one. I think most of you probably can see that 49 is 7 squared. But let's say that you don't know this. Remember what we did before with our change of base here. I can make this a common log and make it a common log of 243, but I would have to divide by the common log of 3. And so now let's go to our calculator here. Got all this stuff still sitting in there. Let's just get rid of it. I'm going to evaluate that. The log of 243, make sure you close the parentheses there, divided by the log of 3. And there you go. Still getting 5. So it doesn't really matter how you got to approach it there.
Convert each of the following into exponential form.
Okay, so in this question here, we're just going to repeatedly practice converting from one form to the other, from the log form to the exponential form. And then later on, we'll go and do this in the other direction here. So here we go. Base of the logarithm is the base of the exponential form. A logarithm is an exponent, so this will be 2 cubed, and it'll equal the argument of the logarithm, whatever's inside the log. So 2 cubed equals 8. That's the pattern. Base to the power equals what's inside. Now over here, the base isn't written, but we already know that if the base isn't written, that means it's a common log, and so that's 10. And so the logarithm is the exponent, so whatever that equals goes up in the exponent here, and it's going to equal the argument. So base to the exponent equals what's inside. Over here, the base is 2, so the base of the exponential is 2. The logarithm equals the exponent, so 2 to the 0, and that's going to equal what's inside the logarithm, so 2 to the 0 is equal to 1. Okay. Now don't get thrown off by the presence of fractions here. Doesn't matter. The base is 2, so 2, the exponent is what the logarithm is equal to, so 2 to the negative 2 equals what's inside the logarithm, the argument of the logarithm. 2 to the negative 2 is equal to 1/4. And if you think about that, yeah, that's true. That negative simply causes a reciprocal to occur, so it pushes that term down, and you'll have 1 over 2 squared in the denominator. So, 1 over 2 squared. 2 squared is in the denominator. Okay, over here, okay, a little bit more abstract because we're just talking about variables here, but if the base isn't written, the base is 10. The logarithm equals the exponent, so the exponent is y. And the power here equals the argument of the logarithm, what it is we're taking the log of. Okay, over here, again, now in this case here, the base is a variable, and that's okay, so the base is a variable. A squared, a to the 2, because the logarithm is the exponent, equals the argument of the logarithm, so whatever's inside the logarithm, so a squared equals 5. Okay, here's another case where we've got this variable in the base, but that's okay. That just means that my variable's a base. My base is a variable. So m to the 5, because the logarithm is the exponent, and it equals the argument of the logarithm. M to the 5th equals r. Now here's the first one that's a little bit different. Okay, the logarithm isn't by itself now on that side. It's got a coefficient here. The first thing I got to do is deal with that coefficient. So this is an exceptional problem here. So the log base 2 of x has got to equal b over 2. Now, honestly, the assumption is by the people putting together the curriculum here is that this is a problem that a lot of you will have. You won't do that first. You won't think about it. Okay? It's an easy thing to do, but it's also a very easy thing to forget to do. And they think that a lot of you will do that. So you've got to isolate the logarithm first so that there's no coefficient. There are a couple of ways to deal with that, but we haven't looked at the other way first. At this point here, we've only looked at kind of this method first here, the conversion. And so now, the base is 2. The exponent is a fraction. Because whatever the logarithm equals is the exponent. And that's okay. Doesn't matter. I can have fractions in the exponent. That's not a big deal. And it's going to equal the argument of the logarithm. So 2 to the b over 2 is equal to x. This last one over here has a similar sort of problem to it, but this time the additional information is being added at the end there, so I need to move that +1 over. Now when you've got something written like this, the assumption is that there are parentheses around that 2x. That's just, that notation means that when it's written in that form, okay? That's just what we're going to assume is true here, but that +1 is outside of that. So the very first thing I'm going to do is move that 1 over by subtracting that from both sides. So we'll subtract 1 and we'll get 1 on the other side here. The base of the logarithm is 3, so the base of the exponential is 3. The exponent is 1 because that's what the logarithm equals. And then the power here equals the argument of the logarithm, so whatever's inside. So base to the exponent equals what's inside. There we go. Whole bunch of practice converting logarithmic form to exponential form.
Convert each of the following into logarithmic form.
Okay, so in this question here, we're going to go the other direction. So now we've got a bunch of expressions written in exponential form. We're going to convert these to logarithmic form. Okay, so here we go. So we look at this 4 cubed is equal to 64. Well, the base of that power is 4, so the base of our logarithm is 4. That should be an obvious subscript here. The logarithm equals the exponent, and whatever the power is equal to, that's the argument of the logarithm. So that's the part that goes inside. So log base 4 of 64 is 3. Over here, the base of the power is 2, so the base of the logarithm is 2. Okay, the logarithm is equal to the exponent, and whatever the power is equal to, that's what goes inside the logarithm. That's the argument of the logarithm. So log base 2 of 1 over 8 equals negative 3. The base of the power is the base of the logarithm. In this case here, because it's 10, I will just write log. The logarithm is going to equal the exponent, so the y there, and whatever the power is equal to, that's the argument of the logarithm. Okay, now this one's a little different because now the power isn't isolated. So what I got to do first is I got to get that power all by itself. I can't multiply this by 4. I cannot make this 12 to the y. You're doing the order of operations wrong. Okay, you can't multiply before you deal with the exponent here. And because I don't know what y is, I can't even deal with the exponent. So that's as good as it's going to get. So the only thing I can do here is bring that over first. But now it's in a nice form and I can work with this. The base of the power is 4, the base of the logarithm is 4. The logarithm is equal to the exponent, and then whatever was on the other side becomes the argument of the logarithm. So whatever that power equals goes inside. So log base 4 of x over 3 is y. Again, there's my power, so the base of the power becomes the base of the logarithm. Whatever the exponent is, that's what the logarithm equals. And whatever the power was equal to, that becomes the argument of the logarithm. So log base 7 of 5 is equal to y. Over here, I've got a power, but I've got a coefficient in front of that power, so the first thing I need to do is move that over. I got to get that power by itself first. And that 2 isn't a part of the base there. Okay? If it's not part of the base, I really should move that over first to make that x squared equals a over 2. So that's another thing you got to watch out for, okay? Just please make sure you do that. Once you've done that though, the base of the power is the base of the logarithm. Whatever the exponent was on that power, on that base here, I put that on the other side of the logarithm, and then whatever the power equals, that's the argument of the logarithm. So log base x of a over 2 is equal to 2. Just that same pattern over and over and over again. The only time that gets a little different here is when you've got a coefficient in front of the power, in which case you just move it over. Okay, isolate the power first. If there's something added or subtracted after the power, just move it over first, and then convert forms.
Determine the value of y in the following exponential equations.
Okay, so now these couple of questions here that are coming from this little question here, number 4, these are good for illustrating why these are so important now. 32 is equal to 10 to the y here. We want to figure out what y is. Well, we know it's not going to be a nice, beautiful little number like 4, because 32 is not a power of 10. It just isn't, right? But what I can do here first is I can convert this exponential equation to its logarithmic form. Okay, I can make this the log base 10. I know that's going to equal the exponent y, so already I've got y isolated, and then I put whatever the power is equal to inside the logarithm. And so now I know that y is simply equal to the log of 32. So common log of 32, and there it is. And just like we did previously, I'll round that to the nearest hundredth right now, so 1.51. So 1.51 is approximately equal to y. So, but the real point here is, notice it's an exponential equation. The thing that I'm looking for is in the exponent, and I used the logarithmic form to solve it. Okay? Over here, exact same thing. I've got this variable in the exponent, so what I'll do here is I'm going to convert this to a logarithm. So log base 10, so I don't need to write it if it's base 10, is going to equal the exponent. And whatever that's equal to, that goes inside the logarithm. And so again, I come over here and I will take the common log of 81. And again, I'll round that to the nearest hundredth. So 1.91 is approximately equal to y. Okay, so it's the idea that I really want you to catch out of this. Yeah, I'm still just converting forms, but I really want you to see that when I have an exponential equation, I'm using logarithms to solve it. And in a little while here, you'll see that when you got a logarithmic equation, you will use the exponential form to solve it.
Evaluate each of the following.
Okay, to figure out these values here, okay, figure out what y is, or what these logarithms are, we're going to take advantage of some of the rules that we've learned here. So first of all, I've got this log base 5, and notice that what I've got here in the argument of the logarithm is actually could possibly a power of 5. 125 is going to be 5 cubed, and then that square root is the same as, okay, it's going to be 5 cubed to the 1/2. And now I've got a power of a power. I've seen this before, so I'm going to take and multiply the exponents together. And so I get the log base 5 of 5 to the 3/2. Now, that is a pattern that I've seen before. Okay? When the base of the power is the same as the base of the logarithm, the answer is the exponent. So this right here is equal to 3/2. Okay, now let's take a look at this next one. A similar sort of problem here. The base is 4. I've got a 64 here. What I want to do here is try to write 64 as some power of 4. And actually, it turns out that's pretty easy because 64 is 4 cubed. And now this pattern is, again, something I'm familiar with. Log base 4 of a power of 4. The result is just the exponent. So log base 4 of 4 cubed is 3. Over here, same thing. This is the log base 2 of, okay, well, 32 can be written as a power of 2. That's going to be 2 to the 5. I still can't make any kind of jump here because this is a log base 2, and I've actually got 1 over 2 to the 5th. So what I got to do is I got to play with that a little bit more. That's okay. This becomes 2 to the negative 5. And now a log base 2 of 2 to the negative 5 is negative 5. So there, my exponent pops out. Log base b of 1. Okay, well, what I got to do here is write 1 as a power of base b. Well, what power of b gets you 1? And the answer is 0. So log base b of 1 is going to be 0. Okay, again, it's the same pattern. Log base a of a to the x, what I had written before here. Okay, now let's do just a few more here. Log base c of c. Now, okay, this one here is really just about being explicit with the exponent here. Log base c of c. What exponent do I put on c to get c? The answer is 1. This is like log base c of c to the 1, and so the answer is 1. And we've seen that before. That was one of the rules we looked at. And now with this one, this is going to get even more clear. Log base x of x to the z, that pattern is almost exactly what the rule was that we looked at before. The answer is going to be z. Okay. Over here, log base 5 of 25. So there's a couple of steps to this problem right here. First of all, in the exponent here, I'm going to change that 25 to 5 squared. So now, up in the exponent, I get log base 5 of 5 to the power of 2 here. So that pattern, log base 5 of a power of 5, they're going to leave me with just that exponent. So that whole exponent is just going to become 2. And then 5 squared is 25. And so now looking at this, 5 to the exponent, log base 5, I got 25. So whatever that was became the final answer. And that was actually one of those rules that we'd seen before. Over here, okay, log a to the log base a of a. Okay, well, log base a of a. Now we saw an example of this just a couple seconds ago. Log base c of c was 1. So log base a of a is going to be 1. So this will be a to the 1, which would just be a. Okay, now I know I went through those relatively quickly here. You can go back and look at them as often as you need there. But it's the same pattern that we're trying to utilize for all of those particular questions in one form or another. So anyway, there you go. Hope that helped.